The thing has been hit. That says that we're alive. Alrighty then. I guess what's going on? Memes here. Yes. Nobody would ever post something as clickbait on the internet. Ever. Speaking about clickbait on the internet, some of you all may have seen this thing going around within like the past number of weeks or so. Scientists observe negative time and everything. So, therefore, we should all totally invest into DeLoreans. Go into debt if you have. This is not financial advice. This is just a satirical thing. Do not listen to me. I am not an accountant. Heck, I'm not even a traditionally trained physicist or mathematician or something. I am a dude here on the internet. But at least read through the Scientific American article, and I've heard another videos and everything. And I don't want to say this is reasons. Like, people don't trust scientists. A lot of scientists, they're saying their science stuff, and to be fair, they're often totally correct, or they're not trying to lie. And then different folks want to communicate things. And since we live in a clickonomy here, yes, that's right. Your attention equals money. Some people may say, oh, maybe we should have it be as unregretted attention. Positions and policies may vary depending on platform. Purpose and existential peas aside here. All right, so what the heck are we talking about? So we'll let folks come in from wherever on the internet where you're coming from, whether you're coming from the YouTubes, the X Twitters, the skies that are below the Discords, some randomly shared thing, or somehow the algorithm thought you might want to hear a dude continually use quotation marks every time he says negative time. I'm not going to always use that, but I really got to try to use that because people say negative time. Therefore, time travel. Listen, this is I think one of those human psychological things. And again, I'm not a psychologist. I'm a dude on the internet, but very often you'll hear somebody say there was an unexplained aerial phenomena. It was an unidentified flying object. Therefore, aliens. Maybe. It might be. It might totally be aliens. Or maybe it's of terrestrial origin. We just don't. My question is, how many observations do we have in beyond the Earth's magnetosphere and stuff? We're not here to speculate about that. Maybe we would need Dr. Salvatore Pyatt, but it's I shouldn't even name drop him. That's probably not a good thing. All right. So what do we? Let me actually address the chat because this seems to be an actual thing that people are interested in. So rather than rambling on about all the stuff that we do and everything, if there's anything I've learned from playing enough Japanese role-playing games, it's you need to cruise around. It doesn't hurt talking about things that are popular, especially all right. You hear that thing? Dr. Hassenfelder had a thing last month where it's like clock in reverse and stuff. It's like, all right, here's what we're gonna do. So for this whole thing, it's like, what did we do? It's well, let's share with the class, shall we? You do the blatantly obvious thing. Negative time in quotations. You got our little eyes looking over. It's like, what? From Scientific American. Evidence of negative time found in quantum physics experiment. This is a quote towards the end of the actual article. Even though the phenomenon is astonishing, it has no impact on our understanding of time itself. But it does illustrate once again that the quantum world still has surprises in store. Why does that kind of sound like it was written by an LLM? It, I mean, I was all for human up until this part. It does illustrate once again the quantum world. That seems like a normal thing you would read on the internet. It's like, you know what? I don't care. If it came from some agent, whether it's human or otherwise, who am I to judge? Unless I'm a judgy judgerton. Yeah, nobody would ever do that. So let's actually see. How do I stop doing this thing? Oh, okay. There we go. There we go. All right. Let's engage. All right, so we had Hex here, and Hex was commenting that negative time. Well, save me if I'm ever late. You're making me really wish it was an actual phenomenon. Okay. But Rick is commenting. Doesn't believe this for a second. I see what you did there. Jax is here and saying, I hate this time of year. If I get some negative time, I can skip some of this old BS. Yeah, yeah, yeah. Travel from the future. Here's the thing. I mean, I can't even say this is why I'm like always late and everything. Well, I'm trying to account for it. No, no, it's just my own poor mismanagement of all this. Dang, I did a presentation in college and stuff. I was making up for 3 credits that I didn't actually do for my HRAP or whatever that thingy study alone pro. All it is, I chose WoW over doing the project, and hence I was on like the 5-year plan or whatever. It's okay. It's okay. Uh, uh, hey, you got AK Shaw. Good to see you. Good to see you. Yes. Well, my time might be worthless. That may or may not be accurate. Oh, we've got the Jolly Duck too. Got the Jolly Duck. We've got the Upcycle crew. Yes. Here's the thing. I see a lot of folks. Okay, sometimes I click on if I have time. Sometimes I don't. I understand. It's like I'm just doing a whole bunch of numbers and stuff like that. If you don't have any interest in numbers, I had a friend I had seen for a long time and everything. It's like, well, how's this stuff going? Good, good. You want to see? No. He wasn't interested. What am I gonna do? Like force him to be, you must watch this. Why? Cause some cult of personality? God, it's not like that's ever gone wrong. Hey Mike. Mike, I'm in Massachusetts right now. Um, I'm very bad at managing time as we can see, because this episode's literally called Negative Time. Um, I'd love to take a look at the lab or maybe have another chat with you again at some point, my man. All right, all right. So what are we talking about? Okay, so let me actually update by erasing the scary numbers and stuff like that. It's okay, it's okay. Uh all right, now for you. God, has it been that long? 2025 now. Yes, it's literally been half a decade since the plague descended upon Earth again. Dang, it's a really crazy thing to think about. Yeah, I guess they weren't kidding when they say time flies. I don't know. Does negative time crawl? Oh, was that a Master Splinter funny? I have to check with Rick on that. But I digress as I continue to erase the speed of light, and occasionally, sometimes answers might be within the questions, as other folks have so eloquently put it. We'll talk about that another day. It's originally what we were going to talk about, but I figured I'm like, I see this stuff and you see all these headlines and stuff, and then people will post headlines, and you get tired of it after a while. So you're like me, and you just stop. You read the headline, you look at who posted it, and be like, all right, they probably have, and that's bad because sometimes people actually say different things than you would expect. Very often, if it's from somebody that makes their business by having a particular opinion, I mean, totally bringing you news fair and balanced in the most ethical journalistic way possible. Yeah, we all saw all that one. Uh, I digress. I digress. Or I'm terrifying people because I'm expressing opinions. Is so I'm not sure how I should feel about this, but it's like when I was at no, we'll say no. It's inappropriate. I was going to say some people recommended that maybe I be a comedian and stuff. And it's like that's not the reaction you would necessarily expect at a funeral, but eh, I guess it makes sense for this. All right, so negative time. What are we talking about? We'll put it on the board. Negative time. We're gonna put it in the little thingies, the quotations. Negative time. All right. Doing this because I have a whiteboard and I feel the necessity to use it. Negative time. We're gonna draw our same little eyes that are like put a little thought bubble. WTF, mate. What? What are you talking about? And I understand. Okay, long story short, they're basically firing a whole bunch of photons into some rubidium atoms and stuff like that, and kind of like the what we use for like atomic clocks and everything. And as it goes through, there'll be an excited state, and that's how we can have like very precise, like, no, I'm thinking of cesium. Do they do the rubidium clocks too? Oh, okay. Well, basically, cesium, they have its, what is it, like, we got about 10 digits to that. It's like 9.9 whatever billion oscillations or something per second. But basically, they're firing these photons into these rubidium atoms. And very often, it's modeled using a statistical distribution. So essentially, once it hits them, it causes the atoms to go into an excited state. Basically, you can measure the electrons going into a higher energy level. Those atoms are becoming in an excited state. So you're imagining it's like you're shooting like your photon through. It's like, all right, we got our laser. Here's our. I haven't even read the paper, so this is probably all wrong, but that's okay. So we got a laser. Gonna shoot our traditional view of photons, little corpuscular things that are totally not corpuscles, but they're waves. Sometimes they seem to be particle-like. All right, we're shooting these things, and then we have our rubidium atoms. We'll make them. Actually, no, we'll do it this way. Actually, that'll make sense. Okay. Then we're gonna model it as like a little circle there, a little sphere. We'll have like a rubidium last, and then these are excited. Why? Because I already started to draw them in the wavy, excited way. And this seems to make sense. We'll put a little photon there. All right, so these are in excited state. So here's the thing. Normally, if you're gonna have like a photon come out, because well, we'll put another laser down here and we'll go. All right. So normally when this interacts with this, it's gonna become wavy, and then it will emit a photon because that electron will end up taking a lower energy level. Okay, so long story short is there's supposed to be a specific amount of time we would typically expect on average get to spend in that excited energy state. What ends up happening is typically after they've already kind of been excited and you're sending photons, some of those photons appear at less time than we would think for it to have gone through the excited states. So that's how, within the calculation, you're looking at it's like, oh, our expected expectation seems to, so it ends up being negative time because we would figure typically, I think a hydrogen atom is, well, these are rubidium, but hydrogen atom is typically light moves or an electron moves at what about 100, 137th the speed of light or something. So it should take some time for it to interact and then be re-emitted. But at some point, it seems to just go straight through. And there seem to be effects where you're like, all right, it goes there and then it's already here. And then there seems to be some lag time between the proposed excited states. Okay. So that's why it was an interesting observation is did we go back in time? No. No. No, we did not. I know. It's a terrible thing. Terrible. Hey, David. Good to see you, my friend. Let's see. Hold on, some other folks. All right, that sounds good, Mike. Uh, where else we? Well, if realities is here's the thing. That maybe it would explain a lot. Jack's commenting if reality is a simulation, there is no paradox. I mean, I don't know which paradox that might explain many things. Uh, I mean, I can't disprove it. Here's the thing, Hex. When it comes to the simulation theory hypothesis, it's like, well, which one? That's the thing. 'Cause a lot of folks will say the standard model is broken. What do you mean by standard model? You think mean the most things that people are saying? Are you talking about for the standard model of particle physics? Are we talking about like quantum mechanics and basic et al? the frameworks that we use there. I mean, seems to work for most of the things there. They managed to use like lattice QCD to like detect the mu anomaly and like have it bang in. They got the data to fit. So, and hey, we were able to throw a lot of smart folks in compute at it. Um, that may raise other questions, but that's not why we're here right now. That's the thing. Are you talking about a computer? Why? No, because we know a computer and stuff. I'm just like, well, if you have a sufficiently high dimensional being and they want to run an experiment, what do we do? Put in things that seem to be running in binary and everything. And then we have these qubit style systems that seem to run all these different things. And then they would take, I don't know, longer than the age of the universe to compute or something like that. And then 2 years later, we do it better with a standard classical computer. But I'm not saying it'll happen this time, but it seems to typically happen. Uh, yeah, that's the thing. What perspective? Are we simulation? I don't know. What's a simulation of God or for God? The linguistics matter there, and no comment. Yes, yuck, yuck, yuck. Oh, can only be one dox. One a dox. Okay, it's interesting. Oh, the Roland Institute. I heard they did that over at Harvard too. I forget who it was. Forget her name. It's one of the professors over there. Apparently, her team had published like 18 years ago or something, and then they got it to like literally, so you could literally walk past light, like it was going slower. And I thought that was a really cool thing. Well, it appears to be a very cool thing, literally. All right. Okay. Cool. Uh, okay. This fact is related to the temporal diffraction. Okay, actually, like I'm not gonna lie. If you're on, this is what you actually do. So I mean, here I'll yeah, just in case you're around, let me invite Mike on. It's like, hey, that's why we have the internet. Oh, hey Dan, good to see you. We might actually get Mike. He actually has a lab, so this is stuff he's much more familiar with than I am. So let me where are we at? So Twitter's Michael. Oh, the lag. The lag is real. I just figure I'm like, oh, he can read through articles, and then every once in a while, it's find. Okay. Let's see. Uh, uh, oh, yeah, we can do that. Actually, yeah, you're a smart person. You don't do the Twitter. Okay, that's where we had connected before. Yeah, let's just do that. All right. Apologies, everyone. Oh. Yeah. It's catching up. We're catching up. Uh, uh, so many interesting. Yeah, I was gonna say if you're. Oh, I think I may have. Hold on. I think I. You know what it was? I'll bring up another browser. I think I did this on my act. I'm so scatterbrained. Hold on. I think it's on the actual memes account on the other one. Sign in. Uh, yes. When you use your internet handle, the means of the structure, because that's how people know you mostly. But then when you actually go to email folks and you use your your actual name. There are we. Okay. Not now. God, why are things so difficult? Here we go. All right. Compose. There we go. All right. Okay. Invite. All right. It's going out. Copied and green. All right. Boom. Oh, there you are. Oh, there you go. Hey, you beat me to it. I'm sorry. I had to go into my other email box for my other account. Yes, yes. Because when you create the brand things over here, it's like, all right, well, I have a brand thing. It's like, well, maybe I should actually have it just in case if something happens. Like, see, this is why a lot of things lag behind legislation and stuff like that. There we go. Hey, good to see you, man. Like, oh, you just hit mute.
Yeah, I had the stream going at the same time, so it would have made an echo.
I gotcha. Oh,
Yeah.
good to see you, man. I'm like, you start going into it. I'm like, well, if he happens to have a minute, I'm like,
Yeah, it's
you
been a
actually
while.
have work in a lab,
Well,
so
yeah, I mean, I'm not doing anything that interesting now. I'm just like filing receipts and stuff. It's very boring, honestly. Yeah,
sounds
but
like a lab.
yeah. So, and also, I was going to mention Mark Sokol is also live streaming right now. He's testing out the 3M invisible wall experiment right now.
Is that the thing where they're like using it to do like hologram stuff, or is it like the
No.
antithesis of that? They're blocking
No.
out
So
things.
basically, what happened was at the 3M plant a couple of years ago. They brought in their electrostatics expert because they were getting this effect where they had a polypropylene roller and it was rolling at some like crazy speed up onto a roller, back down, and being re-spooled. So there was some roll-to-roll processing, and they were doing this at a very high speed in South Carolina, and it was very humid back in like 1995 or 1996. Maybe 1993, somewhere around then. But anyway,
Are you talking like a roller like painting or something?
polypropylene. Like
Oh, so laying laminate because polypropylene is like a very high in grade industrial plastic. I thought.
well, yeah, it's just a roll to roll processing. They unroll the thing, they process it, and they re-roll it up. But
Okay.
anyway, so when they were unrolling the plastic, it was getting a charge of a couple megavolts in the steady state because this guy put his field meter 20 feet away from it, and it was maxed out at 200 kilovolts. So yeah, so it was pretty intense. And so basically, apparently, no one could walk under the roller. Like there was like a force field pushing everyone away from it. So
I can believe that because it's like when I worked at in the warehouse and everything, we would take like the was it the 4 by 5 foot pallets or whatever, and you'd stack them up with like all the groceries and stuff. And then when you go to wrap it, you're wrapping it with like a little thin, like couple micron thick thing of plastic, and
yeah.
you're going around on a dry day, man. I could feel that charge,
Oh
man, and
yeah.
like that was very thin.
Yeah, and so there was multiple things going on there. So like there's the charge buildup. There's also effectively the high electric current because the roller is at a high charge and it's also moving fast. So you have an effectively very high current. And then there's electrostatic discharge when the roller opens up initially. So this roller is moving. This thing's moving at some fast rate, and there's like they had a video of it, and you can see like the like little lightning bolts running across the roller surface. But anyway, so the high rate of electrostatic discharge is one thing, the high current and the high charge and the high voltage, and all of those things together in this strange setup apparently produced this like electrostatic pressure force away from underneath the roller. So no one could walk underneath it. They were repelled.
It had like an electromagnetic shield.
Yeah, more or less. Yeah. So that was interesting.
It had a superpower from Godzilla, the Netflix series.
Yeah, Mark Sokol's testing it right now, although we expect the effect that he's testing right now to be 4 orders of magnitude less, at least. So, but I mean, it's a start, Yeah, it's hard to scale something up to the size of a 3M plant. Although there's up here in Massachusetts, there's a company called FlexCon. Maybe I should get in touch with them again, and they could do some roll-to-roll processing under those same conditions. But anyway.
So this was in the 3M processing plant. They were just processing polypropylene, and they observed this effect.
Allegedly. So there's an article, and there's also so the fellow who allegedly reported this, he wrote a paper about it, which we were able to find, and it didn't mention anything about very high voltage or these electrostatic effects in it. So it might just be some fake news by some other person that's embellishing the story, but we're going to find out anyway. It's an interesting setup anyway.
So the reason you were talking about kind of, I think the effect, because we were talking about like that is those observed things from negative time. And when you go into the actual, like a Scientific American article, and where is it? Oh, this guy. It's so you bring it up. It's like, all right.
Here's Mohinsky's paper with the diffraction in time. I mentioned Mohinsky's paper. Yeah.
But it's just and again, this is just standard. Whatever happens within the internet now, it's with clickbait and everything. It's like evidence of negative time found in quantum physics, and then when you get to the end of the article, it's like, even though the phenomena is astonishing, it has no impact of our understanding of time itself.
Well, I mean, so you're getting a phase shift in the wave as it travels through the rubidium, which is unexpected. But you can have any. So with the signals, you can have phase velocity and you can have group velocity, and you can't have both be infinite, but you can have one be faster than light. So
yeah, this was the paper.
Nice.
That was
I actually haven't read this. I've seen it around. I haven't read it yet myself. So let's.
I haven't read. I only read the Scientific American article.
Yeah, well, this is whenever you see one of those sensationalist articles, just go to the paper. It's much better.
Yeah, it's that way, and sometimes you just control F through it, and it's like, all right, what's the thing that they said happened, and then you get about 3/4 of the way through, and it's like, well, this is a remarkable thing that we did not expect. This does not break physics as we know it.
Well, let's see. Examining the energy transport.
All right.
Scrolling down in the.
So what we have here is from the abstract. When a pulse of light transverses a material and incurs a time delay referred to as the group delay. Should the group delay experienced by photons be attributed to the time they spend as atomic excitations? ? However reasonable this connection may seem, it appears problematic when the frequency of the light is close to the atomic resonance. Oh, see, that's cool. They mentioned things like that. I mean, you get a little woo-woo there, but you're actually talking about science stuff.
Are we though? So that's if you're near the atomic resonance, you're talking about maybe some near field excitation, which could be superluminal. But then how does it turn back into a far field excitation? So that's interesting.
I mean, I was going to link a few more things about studies on water. I had actually another Mike on before, and he was supposed to be working at a lab in Arkansas, but the pandemic hit. Ooh. So he spent 3 years just researching water over the past 60 years. And he noticed that about 3 separate groups noticed this, something about water where it was able to transmit faster than we believed before. And this effect was noticed by 3 different groups in 3 different areas of study. And as far as he could tell, none of them had collaborated or knew each other's work was out there. It's something within the Young's modulus. It seemed to be communicating faster than we would normally expect. But as soon as I read this, at least read through the article, where it's basically, it seems there was an excitation. And once you continue to fire more and more photons, like once it's in the excited state, it seems to move faster.
I know, diffusion equations, whether temperature diffusion or material diffusion equations happen. So the form of the standard diffusion or heat equation is first order in time and second order in space, or the other way around, I forget. But in any case, it's not a second order PDE formally, because it's not second order in both of the terms. So you don't have wave equation solutions to that. If you have
so for noobs like me, that means both terms aren't squared. Only one term is okay.
So you have instead of elliptic or hyperbolic solutions to the PDE, you have just a parabolic PDE. So that means that you have exponentials, but you don't have sines and cosines as your solutions. So if you have that exponential, it doesn't have a concept of speed. So it effectively travels at infinite velocity. And so there have been a lot of attempts to create hyperbolic heat equations to avoid this aberration in the math. But it seems like in some situations, it might be literally true. So that's really exciting because
all I know is I go to my old friend Wolfram Alpha. I look for up the diffusion equation. And it's like, yeah, we're working on this.
heat equation.
So it's not a really easable.
Yeah, just like look at the heat equation. That's a more standard term. Both should work, but it's still. Well, maybe it's maybe
this is a me.
It's on. Yeah, it must be servicing the website or something. Just look it up on Wikipedia or something. Yeah, I that's weird. That's really weird. Yeah, I don't know.
I mean, no, that's a weird thing.
Broken. Okay. Something. Yeah, maybe it doesn't have like AI interpret. Yeah, so it's right there. It's common. It's not difficult. It's not a difficult equation. So something's just broken on Wolfram Alpha right now, probably.
No, I know they've been doing updates. All right, so basically we're relating things, and then one of the things is squared. Basically, it's referring to a partial differential equation.
Yeah, and so this if you have some initial condition that's like this shape they've got, then everywhere in the space will instantly change at the next time step. Everywhere in the space, even infinitely far away from the object, in principle, mathematically at least. In practice, they assume that if there's a speed of light limit to the propagation of classical information, then there must be a wave equation that is at some limit behaves like a heat equation. And so this is why they're looking for hyperbolic heat equations, because they look like they behave as a
it looks kind of like a saddle there. So it's at some point you would observe something that would be weird.
The initial condition, and then it's diffusing. So you have some shape there, and it diffuses out.
No, I'm saying it does kind of look like it's kind of going like that on the edges there when it's melting down there.
Yeah,
it's getting thicker at the bottom.
So this is an interesting part of physics, because either you have to violate the speed of light limit and you have to let it have this heat equation solution, or you have to lose the second law of thermodynamics, because once you have a hyperbolic heat equation, then you have a wave equation solution for temperature. And if you can manipulate that wave equation appropriately, you can cause temperature to bunch up in regions, and other regions will cool down. And then you can harvest that for extracting energy from a single heat bath, which would violate the second law. So there's some types of hyperbolic heat equations that may still have a second law of thermodynamics concept, but it gets really finicky. So is it simpler to just say maybe some hyperbolic equations do exist and then we have faster than light? Or so yeah, like basically, do you have faster than light, or do you have violation of the second law of thermodynamics? That's the question. And
okay, for because when you actually go into the article and everything, and you go back and they start talking about, it's a spooky action at distance, they're doing the standard thing.
Yeah, I mean, this is all boilerplate soundbite bullshit. Just look at the papers. Excuse my French.
Oh no! I hear. Hey, you're entitled to your opinion here. It was a little light profanity. It's okay. Hey, I highlighted other things before. We just try not to be hateful and everything. We attack the ideas. It can be, because when I had to spend some time to read the sentence, and again, I think it's being peer reviewed now. When you see quotes like,
wait, this is the Scientific American. I thought we were looking at
this is Scientific American. I got the article right here. But
the article's next week.
That's where they listed the new study, so we got to give credit. So it took a positive amount of time but our experiments observing the photons can make atoms seem to spend a negative amount of time in the excited state. So basically, what I took is
Oh, okay.
basically,
I see.
normally we're exciting the rubidium atoms. We assume the photon to get it into that excited state is going to take a period of time, and then the photon will exit. So whether it spends 137th of its time or the speed of light or something in that, and it slows down because light would no longer be in a vacuum; it would be in the medium
Okay.
of the material,
I
so to speak.
understand what's going on now. I misunderstood with the temporal diffraction thing, but that's also cool stuff. Okay, so let's.
Because we also had that thing about dark energy being the temporal thing that's been in the news and stuff recently. So
Oh, I
yeah,
don't know about that
people's
either.
minds get really wonky, and that's why
Yeah.
I'm confused about this. So I'm like, all right, let me actually read what it is because I've heard people explain it a couple of times.
Right.
See if
So
I can
this
kind of
is
rock it.
okay. If I understand correctly now, based on what I've seen so far, this looks like it's a. This is a zero index metamaterial. So have you looked at? Actually, yeah. Even just like look up zero index metamaterials and look up some photos of zero index metamaterials. Just real quick.
Uh, Zero index.
Metamaterials. Although the word zero is better. Images.
Okay, yeah, I don't know. Correct to me. All right.
It's an array of posts. It's an array of posts, and if you go look up there, it has zero index when it's in the resonant state. And they were just saying that the rubidium atoms are near the resonant state,
Oh.
have this faster than light property, but it's probably a zero index metamaterial, which means it's definitely a group velocity versus phase velocity thing. But if you check images of this, I'm sure we can see that this effect happens in arrays of posts. Yeah, the first and second and third, and yeah, these all you can see it's arrays of posts. So you have crystal with some structure to it, and once it's in the resonant state, it all goes up and down at the same time, and so that's how it's happening. That makes sense.
Because the way I kind of thought of it is, I remember they had that thing that a lot of folks, I at least remembered as Professor Roger Penrose when he was talking about like the Orco-R collapse thing, and then all of a sudden a study comes out. It's like, well, we seem to have noticed a super luminescent type effect happening within tubulin, which
Hmm.
is basically what they make microtubules out of, and it's like super luminescence. Now, and again,
So
even
there's
Professor
yeah,
Penrose,
that's different. That's super radiant scattering. That's
yeah,
a
super
different thing.
radiance, yeah. But it's I'm viewing it as that, and the analogy from that in my head was the old incandescent light bulb, in that you would turn on, and if it turned off, it would still be radiating for a period of time because it was utilizing the heat in the bulb and was still giving off light. But what
So
I
super
was
radiant
thinking,
scattering is a little different than that. So when you have super radiant scattering, the typical example people talk about is like if you have a spinning black hole, then if you shoot a laser beam around that black hole, if it enters the ergosphere or whatever it was, I forget the exact situation, but basically the spin of the black hole causes frame dragging, and that increases the frequency of the light, and it comes back at you at a higher frequency than you put it in. So, and
because
in,
it was accelerated because it
super,
was angularly and being
yeah,
accelerated.
so yeah, and so you would steal energy from the black hole by decelerating the spin velocity of the black hole by some tiny amount. And so super radiant scattering is when you send in some light, it is then amplified by some store of energy in the material.
So,
But this
oh,
is different than that.
yeah. Oh, no. I was just taking that analogy, and my thought was, doesn't light technically travel faster if it's hotter?
What?
Doesn't or no, excuse me. What is it? Is energy something has a more effective means of transmission when there's more energy present? I realized the words that were coming out of my mouth, and then
I don't know what the question is.
see, I thought basically if if it was oh yeah, here's what it is. So basically, if an atom is not excited, basically within at least the Scientific American article, they were saying it's once it became excited, light just seemed to be doing its normal light thing.
But it's not
Like, it
just
didn't really.
excited. It's not just excited. It's resonant. So
I see what you're saying. Now, once you hit that resonant peak, the photons are just going to do their normal
yeah, so
photon thing rather than having any lag.
a
Okay.
zero index metamaterial works because it is in a resonant state. The transient at the start is not going to have zero index. It's going to be, but then because you're separating group velocity and phase velocity, so you're having a lead in the group or phase velocity because this zero index material is behaving as if it has an infinite refractive index.
Can you explain the difference between group velocity and phase velocity?
I forget it, but let's look it up.
Okay. All right. Because
This is the hallmark of a true physicist. Looking it up in the book occasionally. Let's see. So the phase velocity, let's see, is the velocity at which any single frequency of the wave travels. So if you have an envelope of the wave, which is composed of multiple frequencies, you pick one specific frequency, some component of that, and then it travels at some speed in that medium. So if you have a dispersive medium, so where different waves travel at different speeds, then the phase velocity will be different for different frequencies of the light, and the group velocity is the velocity of the overall envelope shape of the wave's amplitudes.
So
So
phase
one of those can be faster than light, but not both, because you need both of those to be faster than light in order to communicate information faster than light. If only one of those this is a homework problem for folks out there. If only one of these speeds is faster than light, you can show that you still cannot transfer information with the light that way. If only the group velocity or phase velocity is FTL.
Now, isn't this part of that because light is also supposed to be like doing its like twisting and stuff like that, but it ends up traveling at speed of c?
It's because if you have a system with group velocity it gets a little technical, but if you have a group velocity or phase velocity faster than light, then that must happen in some resonant material where there's multiple waves going back and forth, and the overlapping shape of those waves is what's traveling faster than light, but the individual wave components themselves are traveling at the speed of light or slower.
Is that how technically we're supposed to have like potentially conjectured superluminal expansion after like t equals 0 Big Bang and stuff? And is that how that works? Or?
I don't know. These days I'm a flat universer. I don't believe in the Big Bang.
Okay, it's a respectable place to be, my man.
Yeah, well, there's so many other explanations of the Big Bang. First off, if we're in a black hole, then since our light cone is looking into the past, then the stuff in the past hasn't had as much time to fall into the black hole as we have, so it would be going slower into the black hole than we are. So it would appear redshifted relative to us, actually. So that's a possibility there. And then the other thing is, what was the other explanation? I don't know. There were a few others, but that was one that came to mind. I was talking with Curtis Horn about that.
Some people were conjecturing about simulation and stuff like that. The thing that gives me interest in that is just because of how crazy different things happen, at least for me, maybe because I'm a troll and I'm looking for these things. And every once in a while, when something really silly happens, I'm like, if I was a game dev, I would totally put that in there.
Yeah, I get that feeling sometimes too. Like, yeah, pretty much. There's definitely things I've seen that I cannot explain.
I know, and that's what makes me interested in other things, because when you talk to very highly sober folks and they describe things that other folks might be like, oh, that totally ever happened, it's like, how can I say that? I haven't seen that and stuff, and I have no reason to believe that this person is lying to me for any reason. So so back to negative time.
Right, yeah. So what we're seeing here is they're using a time of flight measurement. So they're saying, okay, the light was here and then it gets to here. And so there's some phase in the light. There's some phase in the light, like some like a cosine or sine, like the phase of that. And then the phase on the output
maybe
shifted forward.
can maybe you correct me? Let me hold on. How do I do this? Boom. Okay.
All right.
Let's say we have like a laser.
Yeah.
It's shooting out our totally not corpuscular photons. All right. Rubidium atoms or whatever it is. Excited state, non-excited states, normal circles and stuff. I'm just kind of saying that when it's more excited state, it's just going to continue doing its thing rather than spending its time chilling out or having it
So
spread.
you have a Bose-Einstein condensate there, and so the light going in will have a phase factor of like cosine of kx minus wt. So kx minus wt for the time, and then it goes into the rubidium when the rubidium is at its resonant point. So if it is not yet at resonance, there'll be a time where it adapts.
So we'd still see our standard inertia time.
Yeah. So you initially hit it with
once
this
you hit
laser.
that resonant frequency, the light is just going to be doing its light thing, and the time we would expect it to be spending to get to a united state, it doesn't really matter. It's like superflux.
Well, so inside the material, you've got initially you have a transient. So there's a transient response in the material as it starts to go towards its resonant state, and that transient behaves like normal light. So you get on the other side of the beam as it's going out, you get kx minus wt plus delta, as you would normally expect, delta t, I guess. And so as you would normally expect, you get a lag in the material. And then once it's in its resonant condition, after the transient period, after some short period, once it's in its resonant condition, then you have kx minus omega t minus delta t. So, and that's because inside the rubidium, in its resonant condition, it's like an array of posts, and so it has a zero index. And the cool other effect that should be the case in that situation is at that frequency of light, at the where you have the resonant point, it should since it has a zero index medium, then anything inside that rubidium Bose-Einstein condensate will be cloaked at that frequency.
Could we think of that frequency kind of like at the top of Norton's dome?
I'm not familiar with what's this.
I mean, that's a very. Dan was talking about this, but basically, this is the thought experiment where basically you have what is it? Rather than using the brachiochrome because it looks like this kind of is a brachiochrome there or catachrome where it's the same thing. But basically, if you're at that point, where do you go if you're perfectly balanced?
Right. Yeah, that's different. That's a different thing. That's yeah, I saw that on the internet recently. Someone.
I think what Dan, I think the claim is that this would basically be a way to think about that is that frequency. I mean, maybe. And again, I think this is for gravitational.
For any resonant crystal lattice, you would have these points where it would appear to maybe have zero index, and it might also be dependent on the angle that the light's going in relative to the crystal and stuff like that. But yeah, once you're in the resonant condition, you have waves going back and forth in the block of material, and the sum of all of those waves looks like a flat sheet of increasing and decreasing voltage or current or whatever. And so
kind of something like this. It's just and it's resonant oscillating factor in order for it to do amazing things.
Yeah. Once it's resonant, you can do, and this is why, like for time travel, it probably will only exist once someone creates some sort of resonant system that can be a reference for the time travel, and then any region within that light cone is reachable by FTL while that thing is still resonating. And so you would have some volume of space-time in the Minkowski space diagram where this resonant system is doing its thing, and then inside any of that region, you could have some FTL effect if you have an agreed upon behavior of the resonant system, and if the resonant system does not stop resonating. and so maybe that's possible. But I don't think time travel is possible in other ways, probably. And so, and it also, yeah, if you destroy the thing, then time travel stops working. So that someone should write a story about that. I think that'd be a cool one.
So but I mean, isn't that like what happens, like where we live, like our existence and stuff? Like, isn't that what people say anyway? There's whatever the medium, call it a superfluid, call it the cosmic space fabric. Don't call it the ether. It's totally not the ether, but no ether.
Yeah.
Uh, but basically, there seems to be the medium itself that has a particular resonance that
Well, I don't
coincidentally allows
know.
light to travel at light. So
So,
that's
so like that's the thing. Like,
I threw you another turtle, man. I'm sorry.
if we happen to live in a region of space time that has been modified in this way by some ancient species, then maybe time travel is possible within that region if you know their secret resonant.
To be
thing.
fair, we are travelers through time.
Yeah, and one, yeah, you know.
If one's thinking about well, can we cheat a little bit? I'm not saying it can't be done. I don't see how it can be done.
Me neither. Yeah,
At least the
me
fact
neither.
going backwards, unless you're gonna willing to wait for a while. I don't know.
Well, you would have to define some structure which is sentient, which is a part of this um, resonant zero index material grid. So it wouldn't be like, it probably wouldn't be made of matter the same way we are, but you could build a sentient thing which is a quasi-particle excitation in this weird zero index medium, and then that could go back and forth if it wanted to. Maybe, I don't know.
I mean, that sounds a lot like a crystal in the mind of God, but
Maybe that's
I'm not here to. Actually, I am here to wildly speculate. It's me.
Well, I don't know.
Actually, to be
Maybe that's. I think about that sometimes, and I'm like, that sounds a lot like the what the ancients did in Stargate SG-1. Did you know? Like they ascended, and then they became energy beings, and then they could go everywhere that they wanted to at any time.
And again, this is a different thing, but when talking about things that ancient folks within just humanity as we know it talked about tales about, well, the cosmos runs in a circle because it's obvious, of course. And then Wolfram will occasionally say it's like, when I listen to modern scientists and ancient theologians, he's like, the ancient theologians have an easier time explaining things. Or at least he's like, if I were to bet, so to speak, I would give a nod to the theologians. So I'm not sure if that's a critique or
Well, I
perhaps
mean,
I'm just taking that
Stephen
wildly out of
Wolfram was at
context.
Stephen Wolfram was at the Unlab conference. I was worried that he was going to like badmouth all the second law violator stuff that's been coming out. By the way, there's a new paper on Nature paper. Let's see if I can find it again. But yeah, I mean, he did a good job though. He with his analysis of thermodynamics, he's still skeptical. Well, I wouldn't say skeptical, but he's still wondering if possibly there's situations where the second law of thermodynamics doesn't apply, which is good because there are situations where the second law of thermodynamics does not apply, including this one, if I can find it.
It's very interesting. He believes he now has a more stronger framework about the second law because I think, according to his essay or something back in the day, it's like, well, it's obviously true, and it's like, do we really know this? Before we bring up the article, we need to do the official get out of jail free card for conjecturing so much. So let's bring Stephen
Okay.
Wolfram into the
Although
mix.
this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
It gave me so much joy to play that while introducing Stephen Wolfram.
Oh yeah, that's great. Yeah, no, that's honestly like maybe we colonize the Ruliad, and then that's what the afterlife or God is or something, and then that comes back and creates us. I don't know. It's weird, you know, but Anyway, yeah. So this device here is a direct violation of the second law.
This is a fantastical title. I mean, this makes me want to bring out and invest in quantum crystals right now. This is not financial advice.
Well,
Hermetic
it's all it is.
hydrovoltaic cell stained by internal water circulation. Wow. Okay, continue.
Yeah, take a look at this. It just if you scroll down, there's a picture of a jar, and you just have a capillary structure in it, and evaporation. So basically, there's something called the zeta potential on the surface of any material that's in water, and so that zeta potential will induce layers of different charge in the surface of the water. And if you have a very thin layer of water in a capillary structure, then sometimes as it evaporates, it carries some of that charge with it. And so
Mike, this. Why did this sound like an experiment we heard about 20 or 30 years ago in Utah?
I don't know. Maybe it is that. Well, so there.
This reminds me of cold fusion or the claim or low temperature.
Yeah, no, this is not. This is not cold fusion. This is much easier. All you have to do is get some like catalytic carbon black on a piece of paper, and you put one electrode on the side that's drying out and evaporating, and you put another electrode in the water on the bottom, and you just get a voltage from this voltage and a current from this thing.
Doing the light bulb with a potato.
Yeah, this is like that, but it breaks some rules, so it's naughty.
Oh,
Let's see.
A naughty potato.
Yes. Anyway, let's see. Yeah, no, it directly breaks the second law. This is so, and it's important.
Wait, hold on. That's a very strong claim, Michael. You're saying no, this very fancy naughty potato breaks the second law. Okay, how does it break the second law?
Right. So let's see. Basically, the second law of thermodynamics I should say more accurately, it avoids the second law, because the second law. So the first law, it's basically an energy accounting system. So if there's a new type of energy, you just add it to your list, and then the first law is preserved again. The third law,
since it exists within space-time, any electromagnetic fields, and it's not an isolated system.
So the third law is that like there is one single like agreed upon ground state for a thing, but that's not true because we have bosons and condensates and supercurrents and superconductors. So there's multiple possible ground states for some things. So
not to mean it's on the rotating Earth that's hurtling through the cosmos and stuff like that. So anything that's
I just mean like
if
you chill this thing down to absolute zero, it may have a magnetic field in this direction or in this direction or in that direction. So there's multiple possible ground states, multiple possible supercurrents in the superconductor once you put it in its ground state. So although it's ambiguous whether that counts as additional stored energy that's not in the ground state. So it's a little ambiguous. So maybe that's not the best example, but something about the third law was already disproven, if I recall. But
it sounds like they're trying to maximize the potential for because I look at this and God, I love this diagram so much because it reminds me so much about comparing different Pokemon cards and stuff like that for their efficiency, which are the scale of attack, HP, and stuff like that. And I love this Venn diagram here.
Yeah. So in any case, to get into it, the second law, so I explained the first and the third law. The second law of thermodynamics basically says entropy always increases or stays the same, right? So if you build something that decreases entropy over time, then you've got a second law violator, and it doesn't increase entropy elsewhere, of course. And so,
what part of this violates the second law?
Okay, so the second law, unlike the first or third, is derived. The second law is derived from statistical mechanics. It is not an axiom of statistical mechanics. So it is considered an axiom in thermodynamics, but StatMech underlies thermodynamics. And when you go to StatMech, you need to assume something called ergodicity, which means that all states are equally probable to happen, or at least of the same order of magnitude of probability, up to some, what do you call it? Some Hamiltonian describes the steady state.
Some limit of X with our sum of probable states.
Yeah, so some Hamiltonian describes the average energy state.
So at some point within this, we have to wave our hands and be
that
like,
Hamiltonian doesn't blow up. the Hamiltonian doesn't blow up or have sharp bits. It's a continuous, nice behaved Hamiltonian.
It's going to be a smooth transformation.
Yeah. So
Okay.
basically, ergodicity, in terms of the individual particles, it means that part of the future energy beyond some short time window of that particle does not depend on its current energy. So an example of something that's non-ergodic would be the stock market. So if you already have more money, then it's more likely that you'll have more money in the future. The stock market.
Okay, you have more spikes and stuff.
The stock market is non-ergodic because wealthy people set it up that way to extract money from poor people. But anyway, that's
no, it's just financial fluctuations. That's all.
Yeah. Well, anyway,
just wave our hands, look the other way.
Anyway, if you have money already, you're more likely to get more money in the future because of how the stock market works. So anyway, it's non-ergodic, and you can demonstrate mathematically that this is the case. It's these are non-random statistical fluctuations.
So we're looking for smooth curves and stuff that we can figure out what might be going on.
Well, so anyway, how do you get a physical system to behave non-ergodic? So the way to do that is you add second order or higher order nonlinearity to the system. So there's in Vladislav Capek and Daniel Sheehan's book, Challenges to the Second Law of Thermodynamics, chapters 3 to 5, we have, what's it called? So they use something called, their example system was the Redfield equations describing NMR. So in the Redfield equations, you have the nuclei, and the nuclei are pretty much all separate from each other and far away from each other relative to their size scale. And they're also shielded by a whole bunch of electrons around them that are doing a whole bunch of complicated stuff. So usually the correlations between the nuclei are small, and the effect that they have on each other is small. So any second or third order terms are negligible. So basically, the Redfield equations are used to describe like everything in thermodynamics for some reason, and not just NMR and maybe gases and a few other things. But usually they're a pretty good approximation, but the Redfield equations implicitly assume ergodicity. So when you don't have ergodicity, you can have weird behaviors. In this case, also, when you have strong quantum mechanical coupling and a second order or a third order or higher nonlinearity, strong quantum mechanical coupling happens over very short distance scales. So basically, you need to engineer your boundary conditions, and you need to have thin layers of stuff. And so this is where
you need to account for like the strong force in physics as we know it in order to make sense of it.
No, in general, you need to think about your boundary conditions as being very close together relative to the mean free path of particles in your otherwise thermodynamic system. Basically, you have to go far from the thermodynamic limit. So the thermodynamic limit's large number of particles n, large volumes, and so the large volume implies with that the boundaries of that system are infinitely far away, so you don't have to deal with them. And then also,
I mean, is that a good assumption?
No, not in this case. Okay. So that's precisely what we're saying.
That's why we do this, because without said boundary condition, it's going to be hard to make sense of.
Yeah, exactly. Well, yeah. So basically, if you get to neglect the boundary conditions, the math works out very nicely in thermodynamics. So they just stick with that, and they just work with things.
Is that where some of the gap, or this is just something completely different? Oh, that was the gap. Never mind.
That's different. Anyway. So, and then the other condition for thermodynamic limit is that the ratio of the number of particles n to the volume v is some reasonable number. So basically, you don't have extremely low pressure gases or extremely high pressure gases, because then the thermodynamic limit doesn't necessarily apply.
Could we, to kind of illustrate, I think what you're kind of saying here is, if you're going to model something, you have something, it's at that amount, all of a sudden it heats up. You're going to have this spike in temperature. But if you're going to model this as smoothly as possible, your graph's going to look like this. But it might not be as, depending on how we're framing it. Just be aware of the data that we're getting, because the data may be not as we initially intuited.
Right.
Okay.
So let's see. Yeah, I mean, it looks like. Well, yeah, I mean, this system will show. It will certainly have a power output.
Can we bring it back around? I'm sorry, we've been going for this. I only usually do an hour for this guy.
Oh, okay,
But
gotcha.
long story short is we're seeing, looks like, even according to the article, a resonant frequency happening, and then all of a sudden we're like, wow, there seems to be different stuff going on.
Yeah, sorry, I just did a data dump of a whole bunch of stuff I've been working on, and
Oh no, that was fine. No, I learned a bunch of stuff, but no, it was fun. No, yeah, I'm doing these things where I'm just doing this on like a daily basis now. I'm only going for like usually an hour there,
nice.
unless it's like a more formalized thing. But I figured you were making some comments. We went back and forth. We misunderstood each other and stuff, and we went around. And I learned up more about resonant frequency. So, thank you for that, my friend. You got anything coming up you want to talk about or promote to the folks?
Nope. It's pretty slow at the moment. Oh,
okay. No, I was blowing you up on the big screen, but
oh, okay. Yeah, I mean, yeah, no, it's right now. I'm just trying to. So right now we're spread pretty thin on projects. So I'm just down in the trenches, as it were, getting everything done, and I think in a month or two's time we'll maybe set up some social media and stuff, and start interacting with the broader public. But we're working on cool stuff here. Oh, you frozen there? Oh,
no, I think I've been unfrozen. All right.
Okay.
Well, a little blip and totally not the Matrix and totally not the ether. But with that, folks, Michael Perrone there, and we'll leave you with that. So negative time, maybe a wee bit misleading. So other than that, peace out, everybody.